Okay, welcome to Basic Combinatorics. This is a really fun section to talk about. There's a lot of cool things you can do with combinatorics. And what we want to do is we're going to start with a really simple counting problem. In how many different ways can three distinguishable objects be arranged in an order? So let's think about this, and let's talk about maybe objects A, B, and C. A, B, and C. These are the groups that we want to look at, these three groups. Okay, and so if I look at just A, what can I put with A? Well, I can either put B or C. What about B? Well, I can do A or C. And what about C? Well, I could do A or B. And then if I go back to this top guy, if I look at all the ways I can do A, B, and if I choose B, the only guy left is C. If I go A, then C, the only guy left is B. Okay? If I choose B and then A, the next part has to be C. If I choose B, then C, the next part has to be A. You see how this is working out? Or if I choose C and then A, the last guy has to be B. Or if I choose C, then B, the last guy has to be A. So when I look at all the different ways that I can arrange stuff, there's a total of 6 different things. Here's one way. Here's 2 ways. Here's 3 ways. Here's 4. Here's 5. Here's 6. So 6 total ways. I've got 3 ways to choose my first, and after I choose that, I've got 2 ways to choose the next, and after I choose that, I've got 1 way to choose the last. And when you multiply all those guys up, you get a grand total of 6. So let's talk about Tennessee license plates. There should be an E right there. The Tennessee license plate consists of 3 letters of the alphabet followed by 3 numerical digits 0 through 9. Find the number of different license plates that could be formed. Well, if we talk about this multiplication thing, then let's look at that license plate. We've got 3 spots for letters. 1, 2, 3. And then we've got 3 spots for numbers. 1, 2, 3. Okay? So, if we have no restriction on letters or digits, okay? So the first guy is going to be no restriction. There's no restriction at all. We can put whatever we want in there. Then there's 24 options for the letters. Whoops, 26. Gee whiz. Might help if I knew my English language a little bit better. That's why I teach math. So there's 26 letters to choose in each of these first 3 places. And if I do the numbers 0 through 9, that's 10 items to choose in my last 3 places. And so how do I work this out? Well, just like in that very first problem, I've got 26 ways to choose the first, times 26 ways to choose the second, times 26 ways to choose the third, times 10 times 10 times 10. And so when you punch this into your calculator, in the state of Tennessee, there are 17,576,000 ways to do a license plate with no restriction. So we could have repeating numbers or letters. Okay, but what if they come in here and they go, okay, each letter can only be used once. Each letter used only once. Each number used only once. Well, how does that change our problem? And the fact is, it changes it just a little bit. So we still have 6 spots of information to fill. But now that we can only use a letter once, that first way, we can pick any of the 26 letters of the alphabet. But the second letter that we pick can no longer, I don't have 26 choices anymore. I've got 25. And then I don't have 25 choices anymore. I've got 24. And then the same with the numbers. I've got 10 numbers here, and then 9 numbers, and then 8 numbers. So once you've picked that out, you can't use it anymore. So what do I end up with? I end up with 26 times 25 times 24 times 10 times 9 times 8. And so when I multiply all this out, my number of possible license tags now goes from 17 million all the way down to 11,232,000 different options. And so that's how you kind of look at combining all these different things together in different ways. Okay, so what we're looking at on the slide then are the formulas for finding distinguishable permutations. And if you have n factorial distinguishable permutations of a set of n containing indistinguishable objects, and this is what it looks like: n factorial over n1 factorial times n2 factorial times n3 factorial, and so on. So that's the first line, and that's distinguishable, which is just they're all a little bit different. And then for permutations, that's the gray box. So the number of permutations of n objects taken r at a time is denoted by npr, and is given by the following formula, where you have n factorial over n minus r factorial. And so we want to look at distinguishable permutations first, and then we'll look at how the counting formula works. And so there's a couple examples we'll work, and those will be on the next slide. Okay, so what we're going to look at on this example is the number of different 9-letter words that we can get, even if they don't make sense, just the different ways that we can combine the letters and form a new word. So we're going to look at a permutation as an n set, so they're n factorial permutations of an n set, and then a factorial is, if n is a positive integer, then the symbol n factorial would be the product of n times n minus 1 times n minus 2 times n minus 3 all the way to 2 times 1. So we define 0 factorial as 1. And basically what we're saying is, if we have, like, say, 4 factorial, then 4 factorial is 4 times 3 times 2 times 1. And whatever that answer is what our factorial is equal to. Okay? So with the word dragonfly, we'll notice that all the letters in dragonfly are all unique. They're all different. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different letters in the word dragonfly. And so that means that there are 9 factorial different ways to combine these letters into new words. So what is that? That's going to be 9 times 8 times 7 times 6 times 5 and so on. That means that there are 362,880 different permutations of these letters. Now some of those words will make sense, some won't, but that's how they can go. Okay. Look at the next guy. So we've got, again, 9, 2, 3, 4, 5, 6, 7, 8, 9 different guys. But notice that some of those letters are used more than once. We've got 2 T's, for example. There's 2 T's right here. And so what we're going to do then is we're going to look at 9 factorial. And this is going off that previous slide. 2 things are repeated. So we're going to look at 2 factorial on the bottom. And when we do that math, we're going to get 181,440 different permutations of butterfly. And then lastly, we've got bumblebee. And again, it's 9 letters, but look, we've got 1, 2, 3 B's and 1, 2, 3 E's. So when we look at this guy, then what we're going to have is 9 factorial, because that's the different ways that we can combine all the 9 letters. But now we've got 2 separate groups of 3 factorial each to represent the B's and the E's, which we don't count because we've already got the B once. So then when we do this math and punch it into your calculator, you get that there's 10,080 different permutations of the word bumblebee. So if we're looking then, again, this refers back to our permutation formula from a couple of slides ago. If we look at 6 permutations chosen 4 at a time, then what I'm going to have when I set this guy up is I'm going to have 6 factorial over 6 minus 4 factorial. And you can put this into your calculator, and I'll show you how to do that as well. But what this is going to give you then is 6 factorial 6 factorial over 2 factorial. And we can cancel some stuff out and do this by hand if we want to. But what we're going to end up with is 360. Okay? 11, with this guy would be 11 factorial over 3 factorial. Which, whoops, not 3 factorial. It's going to be 11 minus 3 factorial, which is going to give us 11 factorial over 8 factorial. So if you think about that, really you're going to have 11 times 10 times 9, because all the other parts will cancel out. This is going to end up giving us then for our answer on this guy as 990. And then the last guy is n minus 3. So I'm going to have n factorial over n minus 3 factorial. Now, how do we do this without a calculator? Well, remember what a factorial is n times n minus 1 times n minus 2 times n minus 3. Well, what's going to end up happening is from the n minus 3's all the way down will cancel out. So this guy's actually going to be n times n minus 1 times n minus 2. Okay? So, talking about this, we've got 16 actors answering a casting call to try out as roles, try out for roles as dwarfs in a production of Snow White and the Seven Dwarfs. In how many ways can the director cast the 7 roles? So basically, we've got 7 spots to fill. So if you think about this, we've got 1, 2, 3, 4, 5, 6, 7 spots to fill. And cramming into those 7 spots are 16 different people. So basically what we're looking at is how many ways can we choose 16 people to fit into 7 spots, which is going to be 16 factorial over 16 minus 7 factorial. Which means that there are 57,657,600 different ways to cast those 16 people. Okay, now we're going to look at combinations. So combinations have this form right here, NCR, which is equal to n factorial over r factorial times n minus r factorial. And what this is the number of combinations of n things taken r at a time. Okay, the number of n combinations of r things, n objects taken r at a time. Okay, and so let's just look at some of these and see how it's looked. By the way, it's very possible that you could see this denoted in your book like this right here. This is the same thing as a combination. Okay, so anytime you see this formula right here, we're going to use this formula right here. Okay, so a president, vice president, secretary are chosen from a 25-member garden club. Okay, so what do we do? Well, this is what's called a permutation. Okay, so if we're going to try and tell whether it's a permutation or combination, you know, this is a permutation. There's an order to it. Okay, there's an order to it. We're looking for a president, a vice president, and a secretary, and there's only one way that we can get all of that organized. There's only one specific person that can be the president, vice president, and the secretary. How about a cook chooses 5 potatoes from a bag of 12 potatoes and makes a potato salad? Well, this is a combination. Okay, it's a combination because it doesn't matter which 5 potatoes the cook pulls out of the bag. Potatoes is potatoes is potatoes. Okay, so the order then is not so important at all. Okay, what about a teacher making a seating chart for 22 students in a classroom with 30 desks? This is a permutation. So this last guy right here, he's also a permutation because order matters. All right, different order of students in the same seats results in a different seating chart. Okay, and so that's how you can kind of tell, whether something's a combination or a permutation. A combination, order not so important. Permutation, order is. Okay, so in a Miss America pageant, 51 contestants must be narrowed down to 10 finalists who will compete on national television. In how many possible ways can the 10 finalists be selected? Order matters. So the order matters at the end, okay, but it doesn't necessarily matter at the beginning. So when we look at this, then we're actually going to look at a combination to narrow it down to the 10 finalists. It doesn't matter what order those 10 finalists are chosen. It just matters after that who gets first and second, third, and so forth. So basically what we're looking at is we've got 51 things, okay, 51 items, 51 girls, all right, and we've got 10 spots. So we're going to look at 51 different combinations taken 10 at a time, which is the same thing as 51 factorial over 10 factorial times 51 minus 10 factorial. Okay? And you can also punch this into your calculator, and I'll show you how to do that as well, and you can see that that's happening. And what we're going to end up with then is there's 12,777,711,870 different combinations of girls. Okay, and that's how we can narrow down our 10 finalists. All right. Well, what about the Georgia Lotto? The Georgia Lotto requires winners to pick 6 integers between 1 and 46. The order in which you select them does not matter. Indeed, the lottery tickets are always printed with the numbers in ascending order. How many different lottery tickets are possible? Well, you've got 46 items to choose from, and you're choosing them 6 at a time. So you're looking at 46 combinations of 6, which is 46 factorial over 46 factorial times 46 minus 6 factorial. And when you get done doing that, you end up with 9,366,819 different ways to choose your lottery ticket. Okay, so now we're at Armando's Pizzeria, and he offers any combinations of up to 10 different toppings, pepperoni, mushroom, sausage, whatever. And we want to know how many pizzas can be ordered if we choose any 3 toppings. Okay, if we choose any 3 toppings. So it doesn't matter how we choose those 3 toppings. We just need those 3 toppings. All right? So, for example, a sausage, pepperoni, mushroom pizza is going to be the same as pepperoni, mushroom, sausage. So we're just looking for different combinations here. And this is going to be, if we've got 10 guys that we have to pick from, okay, we've got 10 objects, and that's my n, and we're choosing them 3 at a time. So I'm going to have 10 combinations chosen 3 at a time, which is 10 factorial over 10 factorial times 10 minus 3 factorial. And when you punch that into your calculator, you get 120. Okay, what about if you, whoops, that should be 3 factorial, not 10. 3 factorial times 10 minus 3 factorial. There we go. Okay, so when you punch that in, you get 120. Okay? What if we can choose any number of toppings from 0 through 10? Okay, so what we could do is we could add up like all the different ways to do this. So this would be, if we call this part A, this would be part A. I'll do the second part in green. So here's B. So basically we could add up all the numbers of the form, and we would look at it this way. 10 combinations chosen R at a time, where R would be equal to 0, and then 1, and then 2, and then 3, and then all the way up to 10. Okay? And there's a lot of different ways that we could do this, but there's 10 options. And so what we can do is we can choose, like, for example, if we line up the 10 spots, we could choose like an on or off, like a yes and a no, and a yes and a no. And it would be like, yes black olive, no pepperoni, yes bacon, no prosciutto, yes black olive, no green olive. And we could turn them all on and off and on and off and on and off. Well, how many choices do I have for each spot? I've got 2 choices that I can make in each place. And I've got 10 places to fill. So basically, what I end up with is 2 to the 10th power, which is going to be 1024. Okay, and so if you're looking at something where you could have 2 different ways to pick from all the items, then you could just look at 10 being the number of slots would be our exponent on 2.